Our second plenary presentation is given by Mr. Victor Penn of Xilinx, entitled Adaptive Intelligence in the New Computing Era. Let me briefly introduce Mr. Victor Penn. Mr. Victor Penn is President and Chief Executive Officer of Xilinx Inc. and serves on the Board of Directors. Penn has more than 30 years of experience defining and delivering leadership technologies across FPGAs, SOCs, GPUs, high-performance microprocessors, and chipsets, and microprocessor IP products. Since becoming CEO of Xilinx in February 18, Penn has rolled out plans for a transformation to address new markets with new technology, underpinned by the Adaptive Compute Acceleration Platform. Prior to this, he was Chief Operating Officer and managed global sales, product and vertical marketing, product development, and global operations and quality. Prior to this, he served as Executive Vice President and General Manager of Products, where he led the definition, development, and product marketing of the company's portfolio of products and differentiated technologies, resulting in 3 consecutive generations of core product leadership and significant industry breakouts in integration and programming. Penn previously served as a corporate vice president of the graphic product group Silicon Engineering with AMD and was a leader for AMD's Central Silicon Engineering team, supporting graphics, console game products, CPU chipset, and consumer business units. Prior to this, Penn had executive and engineering leadership roles at T0 Technologies, MIPS Technologies, SGI, and Digital Equipment Corporation. Penn holds 4 U.S. patents and served on the board of directors of the Semiconductor Industry Association and KLA Corporation, a developer of industry-leading equipment and services for electronics industry. He earned bachelor's degree in electrical engineering from Rensselaer Polytechnic Institute and a master's degree also in electrical engineering from Cornell University. Please everyone join me welcoming Mr. Victor Penn.
Good morning. It's a great honor to be presenting at the 2021 ISSCC and the first one that's being held virtually. And for that matter, I should probably also say good afternoon and good evening to you all. So I'd like to thank the conference chair and the organizers for giving me this great opportunity. And what I'm going to do is I'm going to share my thoughts on the role that adaptive intelligence is going to play in the next era of computing. And in this context, I'm talking about computing writ large, which, by the way, I think we've already started this next era. So in this era, hundreds of billions of intelligent devices that will be connected will be generating zettabytes of data, mostly unstructured, from endpoint devices to the edge and in the cloud, and for that matter, the transport infrastructure in between that. And that's going to require a huge amount of more capability and performance as well as bandwidth. I believe in the long run, adaptive computing is going to play a very large role in all aspects of the data generation, transport, processing, and storage. And there are 3 reasons for this. First, the rate of change of virtually everything is increasing exponentially. We can only have to think about, like right now, the COVID pandemic has driven an enormous amount of change just in a short number of months. And we really haven't even seen all the change that this is going to stimulate, and it's going to take us years to sort of see that. That's just one example of one event that's causing an increase in the rate of change. The other reason is adaptive intelligence supports domain-specific architectures. I talked about how the performance requirements at every level at endpoint, the edge, and the cloud is increasing by factors 10x, 100x, in some cases even 1,000x. And that's just not going to be done with traditional compute architectures. It's really going to require many different architectures that are more optimized for the different types of workloads. And the third reason is adaptive computing has the scalability to be implemented in endpoint kind of applications as well as the edge and in the cloud. And there's a tremendous amount of scale that you're required, and not only that, but even after you've deployed this infrastructure at scale, you want the ability to make some changes after it's been deployed, including optimizing for new applications and workloads. So let's dive a little deeper into scale, and let's take cloud, for instance, because I think everybody understands how cloud needs to scale up in performance in terms of the compute node capabilities, but also the capacity of all the storage and the memory. And you also need to scale out, because a lot of these applications really are running over very massive data sets that can't be held in just physically local storage. And also you might want to take advantage of a tremendous amount of compute capability that's available in that. So what you're going to need is to bring together all those compute resources and storage resources with high bandwidth connectivity as well as low latency. So I think everybody kind of understands scale up and scale out. I picked cloud infrastructure, compute infrastructure, but that goes for also things like 5G communications. But you also want, ideally, technology that can scale down. And by scale down, I'm talking about being able to be used in applications like endpoint devices, smart sensors, as well as edge processing, whether that's a computer or that's a product like a car, right? And these endpoints and edge devices have a very broad range of different applications and use cases, but what they do have in common is that all of them are typically more cost and power constrained, and they have to still have a significant amount of capability, but they need to deliver that with low latency. And because of those cost and power constraints, the efficiency is really important. So again, in this future era, you're going to need to have tremendous scalability to scale up, scale out, as well as scale down to build this pervasive intelligence. The other trend is that processing is going to be happening all the time, not just when processing data is going to happen all the time, not just when that data is actively being used by an application. We see processing being necessary even when it's at rest in storage. I mentioned how much of the data being generated real time is unstructured. So you might want some processing happening in the background to actually create structure around that data. You also might want to process the data while it's actually in flight across the network. It could be like doing deep packet inspection for security purposes. So you're going to be processing this data when it's being used by an application, when it's stored, as well as in motion. In addition to having this need for scalability up, out, and down. Distributed adaptive computing allows you to do all of that, and I'll talk about why that's so next. Okay, so let me explain why adaptive heterogeneous architectures, because these devices are actually inherently heterogeneous themselves, really do satisfy these requirements for the next era of computing. And by the way, I consider this a category of products in and of itself. Talk a little bit about the taxonomy. FPGAs are clearly hardware adaptive architectures, but when we added the SOC to the FPGA, you'll hear me refer to that as an adaptive SOC. Our most recent product, Versal, which is the graphic here, and I'll go into a little more depth, takes that to another level. So sometimes we refer to that as Adaptive Compute Acceleration Platform, or ACAP for short. But just think about that as a really turbocharged adaptive SOC. Okay, so why these products really meet the future needs? Once again, you have this tremendous versatility. So it can really be used and is indeed being used in multiple markets, in multiple applications and use cases. And that includes, compute, but also connectivity and, throughput. That includes different forms of AI. Obviously, these devices can scale. Talked about that. We are being used in smart sensors in things like cameras, in cars, but we're also being used in edge devices and in the cloud, so it has that scalability. And then, of course, it runs in all kinds of different environments, including out in space. And it has the ability to accelerate not just AI. There are a lot of chips being developed today and new architectures that are targeted specifically for accelerating maybe just a set of neural networks or a class of neural networks. With this flexibility and adaptability that we have, we can accelerate a pretty broad set of AI, not only machine learning, but other forms of AI, but also the non-AI kinds of processing that are going on, right? Typical applications aren't just about running a neural network. In fact, the applications we're seeing are getting much more complex. They have all different kinds of processing, things like taking in inputs from multiple sensors, fusing that, doing other kind of processing, in addition to multiple different neural networks. And then, of course, because of this adaptability, that you could change the hardware architecture even after you've deployed it in the field. This allows you to deliver new capabilities, new optimizations, new innovations very quickly to market, and it gives you the ability to future-proof these deployed systems. But if I were to emphasize one thing, you hear me talk a lot about this power of domain-specific architectures, is what you're really doing is you're adapting the hardware architecture and optimizing it for the application that you care about, as opposed to the other way around, where the application has to be adapted to a more fixed architecture, something that has maybe a fixed memory hierarchy, fixed data flow, which is often quite non-optimal. And that can really give you factors of performance and power efficiency improvements. So that's one really key takeaway in this. So this is our 7nm Versal, which we actually presented at last year's ISSCC. It's fabricated at TSMC, has 37 billion transistors. And you can see it has a multi-core ARM SOC, dual A72s, as well as other real-time processors, multi-level caches, and other peripherals. There's the advanced FPGA fabric with 2 million logic cells and 158 megabits of distributed memory. There's also a new architecture at the top of the chip that in this case has 400 of these programmable vector processors that also has other kinds of programmability in terms of how it can be connected up. We also have very high-speed SerDes and parallel I/O. There's 44, 32 gigabits per second SerDes that could do things like Ethernet, PCIe. And there are 4 programmable memory channels that can run DDR4, LPDDR4, as well as other kinds of memory, and up to 4.2 gigatransfers per second. And there's also a hardened network on chip, a NoC, that's really important to connect up all these blocks and run high performance efficiently, moving data across the die, but it's also very important for linking some of these kernels that could be swapped in and out of the programmable fabric, which I'll talk a bit about later. So those are some of the features of our Versal chip. I'll walk through some applications on Versal in a moment. But if I were to take this up a level and talk about what are some of the key characteristics of this product category, not just Versal, but any advanced adaptive SoC architecture, you obviously have to have that advanced FPGA fabric. You'll want to have scalar processing capability, so the SoC. You will often have things like a vector compute capability, the AI engine I mentioned. The NoC is very important, the network on a chip, to help with linking and connecting and communication, the data flow on the die. You also need high performance I/O and connectivity for data movement off the die. And what this collection of flexibility gives you is the ability to do both what I'll call spatial compute as well as temporal compute. I'll go into that in a moment. And remember, this is all about not only optimizing the compute capability, in other words, the data paths, if you will, but also the data flow, so how data flows both on chip, off chip, and the whole memory hierarchy. This is really critical not only for performance, but also for power efficiency. So let's talk about in a little more detail. When I talk about spatial compute, what I'm talking about is leveraging the inherent parallelism and the spatial locality of some of these applications. In fact, some of the applications of the future are really demanding and really are more amenable to spatial architectures because they're really streaming applications. By temporal computing, what I mean is the ability to just have present instantiating die, if you will, kernels or functions that are just needed at any point in time, and the fact that you can swap those kernels in and out dynamically while the chip is running, and we call this capability dynamic function exchange. And once again, that NoC is really important. That's always enabled, but that enables a lot of this dynamic instantiation and interfacing between all these different modules. So let's suppose you have an application and it has within it functions A through H, and you recognize that you can accelerate the application performance by instantiating some of those functions into the fabric and arrange that to take advantage of spatial locality, right? So the data flow The positioning of all the memory that's needed is very local, and so you minimize data movement and drive up performance. Some of those functions might work well in the vector array processor I talked about, or just on the SOC, the more scalar processor. And then taking advantage of this DFX capability, this temporal computing, at another point in time you might need different functions instantiated in that fabric or instantiated in the vector array and in the scalar processing. So you can see how in this one architecture you can leverage both types of locality, spatial and temporal, and that really gives you very high performance as well as power efficiency. Some examples of applications that take advantage of this are streaming applications like video, data analytics, and other things. And certainly there are other applications where you can take advantage of time multiplexing of functions. And just last mention in terms of the NOC, I mentioned how it really is critical for enabling this, this allocation of spatial partitioning and even temporal partitioning. You could see you could put these different kernels in separate spaces. They're isolated from each other. They can be configured independently at different times. You can configure the NOC to support those different kernels. And at the same time, what that does is it does pretty much decouple some of the details of the interfaces of those kernels, but it still allows them to be dynamically linked. Okay, now that's at a general level. Next, I'll talk about some applications in real life on a Versal chip. All right, the first application I'll walk through is 5G infrastructure. I think everybody knows that we're in the process of deployment of 5G. We're still relatively early, but it's being deployed today. And 5G is an incredibly ambitious upgrade. It's not just one standard. Indeed, it's actually multiple standards. It encompasses multiple different types of technologies. And so really, it's going to take several generations of equipment to roll out all this capability. In fact, some of the techniques and, of course, even the standards are still evolving. And there are many form factors and many different systems, so scalability is really important even within this infrastructure. You have small cells, you have macro cells, you have very large antenna arrays, indoor, outdoor, all kinds of things. And the bandwidth is increasing dramatically, right, from tens of megahertz to hundreds, multiple hundreds of megahertz. So the complexity, like look at the complexity of a radio of something like this with massive MIMO antennas and so forth. The complexity increases by easily 40x. And if you look at one type of method that is used in 5G to increase bandwidth, beamforming, which I'll talk about in a little more detail, you could say the complexity there increases over 300x. And while the performance is increasing, there's also a drive for yet lower latency, so 10x lower latency reduction to enable applications like IoT and other kinds of real-time applications. And I think everybody knows that you have this huge performance demand, but performance is a two-sided constraint because performance is also driving a lot of power and thermal issues. So thermal efficiency while you're delivering this performance is super critical. The acronym there, SWaP-C, is size, weight, area, and power. All that gets driven and affected heavily by thermals, and that's certainly important, not only in wireless infrastructure, but many other applications. So this is a very challenging problem, and adaptability is being used. So as I said, I'm going to talk about the beamforming specifically. And this is a technique that allows better efficiency by directing the signal energy from the transmitter towards exactly where the receivers are. And again, this gets used in many of these large antenna arrays, MIMO systems. And really, this requires a tremendous amount of linear operations, linear algebra. So if you look at the graphic on your right, the downlink is really a matter of processing the transmit signal on these multiple antennas. It's a weighted sum of all those layers. The uplink is the equalized signal on each of the layers. In some linear combination, the signal is being received on the antenna. So all this requires a massive amount of matrix multiplications, and the size of the matrix actually depends on the number of channels, the number of antennas. So you can see how this complexity will scale with a larger array and so forth. And again, performance requirements, processing performance requirements goes up by 320x relative to 4G. graphic on your left really shows how with a relatively small number of versatile devices, you could do all this beamforming as well as the digital front hauling with the same device. And I'll show you next looking at just the device doing the beamforming functionality. And you could see that this really is kind of a streaming kind of application, right, where the processing is happening, different types of processing functions are happening in sequence. And so what that looks like instantiated on a versatile product is you have all the heavy lifting, the matrix multiplication happening in that array of vector processes I mentioned, the AI array. The functions like digital up conversion, the FFT processing, down conversion, and so forth. Coefficients for all those matrix operations are generated real time in the programmable fabric. And of course, again, the data for the coefficients as well as what's in the array, the data is placed optimally in the distributed memory, both in the array as well as in the fabric. And then the ARM processor, of course, is used for coordination and for message processing and so forth. And so this is a good example, as you can see, of the spatial processing talking about, because the data really pretty much, the signal path does really flow through the chip. So the next application I want to talk about to illustrate temporal, taking advantage of the temporal computing capability, that DFX function, is automotive requirements. I think everybody knows that the automotive platform is being disruptive, and we're moving from level 2, level 3, so a very advanced driver assist, all the way to full autonomy. And that really creates a tremendous amount of compute requirements. But cars actually have multiple modes of operation, if you will. There's, before the car is even moving, when a driver, say, approaches the car. There's also when you're pulling out of parking or into parking. And then, of course, there's driving on streets and highways. And you also have to deal with multiple dynamic changing environments, so weather conditions and environmental conditions. So this is a perfect example of where having different types of capabilities or functions varies over time during operation. And of course, the performance needs are very high, as well as you also have needs like safety and security. And I think everybody knows that today that there's a desire from the industry to do over-the-air updates for things like fixing security issues, but not only that, but maybe delivering new capabilities and new experiences, driving experiences. So let's just look at how this temporal computing or dynamic function exchange is used. If a driver is approaching his car, you might have kernels that execute facial recognition, other biometrics like iris detection. If there's virtual keypad, virtual keypad. While that's happening, obviously the car isn't in motion, so you don't need all the things that are required when the car actually starts moving. Once the driver gets in the vehicle and starts the car and does start to move out of the parking space, then you can instantiate different execution kernels, right? Things like object detection, camera, surround view kind of application, and other automation for moving in and out of parking spaces. And then lastly, once it's up into driving mode, you go through streets, you're on highways. Now, obviously, you need things like cruise control, braking, lane keeping, and so forth. So you could see how through the different modes of operation, being able to swap different acceleration kernels in and out. And by the way, some of these could be different types of neural networks as well. That often is in these applications. You could do that and really get, again, a very power efficient, cost efficient, and very flexible architecture on a platform that you want in the future to be able to update perhaps over the air, not only firmware, but literally changing some of the hardware capabilities. The last example I'm going to go through is not really a specific application. I'm going to talk about how I see adaptive computing being used in the future data center. So we talked about how clearly the data center needs to scale up and scale out. But I'm going to talk a little bit about how the processing in the data center is going to happen throughout the whole data center and more continuously. We see data being processed not only when it's in use, right? When procedural code is perhaps doing things in the CPU, and then you might do offload with a compute accelerator, but also what's in motion, right? So that could be the smart NIC offloading the CPU, not only running driver code, but actually doing computation or things like deep packet inspection for security purposes. It could also be computational storage where you're doing computing when the data is at rest, talked about in the very beginning how most of the data that's being generated is unstructured, so maybe in the background you're changing that to structured data. So really you're going to need this ability to process data, whether it's in use or in motion or at rest. The other thing that you need to do is, because again, all the computing is not going to fit just in one node or a small localized collection of nodes, you need to be able to scale out across the entire data center. So of course you need very high speed interconnects with low latency, and you need to be able to coordinate all these different acceleration nodes, the traditional CPU nodes, and also with storage. And once again, adaptive computing can do that. It can play in all these different applications, and it could really tune the kinds of connectivity or network characteristics that you need for the traffic. And as things change over time, you could also change the optimizations that you want. And then, once again, if you kind of look at this, is that today there's a lot of people doing special kinds of accelerators dedicated for only certain kinds of applications. But that would mean that you'd have to provision, fixed kinds of accelerators, and how you would then coordinate across the whole data center gets a little bit more constrained. In this model, if you look at that graphic, what you have is a homogeneous set of programmable compute acceleration that can be provisioned on the fly with these instantiations of different domain-specific architectures or domain-specific algorithms. So really, again, this flexibility, this dynamic ability to adapt for the actual workloads you have running in your data center is a very powerful model, and it also makes it a more simplified physical hardware architecture. Two other trends that we're seeing happen already, one is just that whole offload of compute that we talked about. Today there's already a lot of people doing, typically through a PCIe kind of acceleration card, closely coupled with the CPU node to do the compute offload, and then you might have some, again, computational storage doing some computing offline in the storage, and then you have SmartNIC that could be offloading the CPU and also perhaps doing other kinds of real processing. So we're already seeing this being deployed today. With these adaptable products that we're talking about, is that really you can simplify that even further and have that one adaptable capability that could do both compute offload, can do that SmartNIC kind of capability, as well as even coordinate directly with the storage to do computational storage. The second trend that's depicted at the bottom is this whole notion, again, this is already there, is disaggregated computing, or really composable computing, which again, when you have all these different resources of traditional CPU nodes as well as accelerator nodes, smart storage devices and the network, what you want to do is for any given workload, collect up and provision dynamically the number of compute and accelerator nodes that are necessary, the amount of storage and the network resources, then run that, and then when that completes and you swap in other networks, you want to, again, optimize things on the fly for all those things. And again, that really makes this disaggregated, but still kind of optimizable on the fly kind of architecture, very, very powerful. And that is not yet realized, but we definitely see that or things moving towards that as a trend. Okay, so on to challenges. These challenges aren't necessarily specific to adaptive computing. I think this is challenges in general. In the interest of time, I'm only going to hit a few. There are many, many more challenges that we in the industry are going to have to face. But as we see, Moore's law is slowing down. I would argue from an economic perspective, it's more than just slow down. There are other forms of integration that are being driven today. 2.5D integration with silicon interposers or other fine-pitched fan-out kind of advanced packaging technologies to moving towards truly active and inactive die stacks. That's really going to be needed in order to deal with this tremendous need for greater compute and bandwidth and so forth. And that's really going to take a lot of changes, not only in the technology to drive the cost down of some of these technologies, but also things like even the supply chain and other kinds of design methods and strategies. Ultimately, even with that amount of packing, then you're going to run into other bandwidth issues, and so we'll have to look at things like silicon photonics embedded in this packaging as well. You heard me talk about thermal and how that's such a big issue in 5G infrastructure, but it's really a big issue in so many different other areas, right? All those intelligent sensors in the car, of course, and other areas. So I think there's going to need a lot of innovation in how to manage thermals and power. And that's going to be materials, architectures, system design, and so forth. And as we get greater density of compute in these form factors like 2.5D integration, 3D integration, once you figure out how to remove the heat and the power, you also have to figure out how to deliver the current needed for that. I mean, you know, you're talking about these devices that are in hundreds of watts and even approaching 1,000 watts. It's no small thing to deliver with integrity the power to that and support that during operation. And I'll just touch on one thing that's above more the silicon level, and that's security. I think everybody understands the critical need for cybersecurity and secure root of trust and things of that nature. But as more of our infrastructure and devices that we use on a daily basis in our life, you know, IoT, smart cars, smart homes, and so forth, security for physical security becomes, you know, equally important, right? The attack surfaces that we're going to have when the world is truly pervasive, connected, and intelligent is just enormous. So this is going to be really critical. But again, this is just a few challenges. And as daunting as they are, I'm completely confident that with the talent and the creativity of the people in this room and our industry, we'll get through these challenges. So look, you know, the new computing era is actually here. We're in the early stages, but we really are building the pervasively intelligent and connected world. And I hope you understand why we believe that adaptive computing can really address many of the challenges of this new era. And it's really an incredibly exciting time to be in the industry, right? Like all the old methods and architectures are breaking down. Moore's Law, which has served our industry for decades, is actually straining. And this is going to drive new innovation, new architectures. And I think, you know, being able to innovate at the architectural level with domain-specific architectures, being able to innovate from a technology perspective, dealing with the software challenges, this is all going to create tremendous value to help us do things like cure the pandemic, deal with other grand challenges like climate change, but not just deal with problems that also create value, but improving people's lives. And I can't think of anything more meaningful that you or I can be a part of. So I think it's just a great time in the industry and really look forward to meeting these challenges together. Thank you.